answer the question.
On the one there? Okay, well, let's do that first too. Joe, what's your question? Which one are you looking at? Physics 30, forces and fields, assignment number 1. Okay, go, Joe, which one? Which one? Didn't we talk about number 1 yesterday?
Yeah.
Oh, should we talk about it again, or? Okay, I mean, when you guys look at my answer key for number 1, hey, now, you guys should have told her that in your classroom, you guys mark a lot of your work. Someone should have said that. One of the things these guys do is they'll mark a lot of their own work. So there's answer keys over on the side wall there, and when they finish doing like an assignment or something, I have them mark their own work. So you guys know for question number 1, really I'm looking for one word. Okay, what is the one key word I'm going to look for in number 1? Conduction. Yeah, I'm looking for you to talk about conduction somehow in there. The idea that charge is going to be passed from the nozzle to the droplets, or which way. You should talk about the electron flow, but at some point in there, you got to talk about conduction, right? If you miss conduction, you've missed the question. What would the key word then be for number 2? Yeah, at some point on number 2, you should be talking about induction. Probably a diagram or an explanation. Right? Those are kind of the main ones. Number 3, why don't I bring up number 3, but we can't actually answer it yet, but we're going to do it after this lesson. So number 3 basically gives you 2 different charges here and a distance in between. Okay. Now, do we know the amount of each charge? No, we weren't given that information. But we could still talk about a field a little bit later. So why don't we come back to number 3 after we finish our lesson? Does that work? Okay, cool. Well, let's give it a try. I think I already started recording, didn't I? Yeah. Okay, topic 3. So, yesterday we started what I thought was like the first of a 2-part lesson on force versus field. Okay. If I were to ask you to define a force, could you do it? What is a force? What's the grade 10 definition? It is a push or pull, right? So, now when I think about different sorts of forces in everyday life scenarios, if I throw my keys, I kind of push them towards you. When I bring them back, I'm pulling them away. That'd be like an applied force, right? And in a way, doesn't friction kind of oppose your applied force almost all the time, right? So when I throw my keys through the air resistance slows them down, right? But that all more or less fits into what we call the Newtonian or classical physics. Things that are, I don't know, they're very logical and intuitive. We have all of these formulas that fit them. We're trying to figure out the motion of projectiles or of free body diagrams of objects. You know what I'm talking about here? That sort of stuff we did in physics 1. Right? Where we're leading to now are some of the more strange and unusual things, where we're going to talk about light and the EMR spectrum and how that sort of stuff works. Because really, for example, we're going to talk about how solar panels work later. Isn't that more of like an action at a distance, if I want to quote that phrase again there? Where light comes from the sun and it magically hits us and it does stuff like grows our food and makes our solar panels work, right? Isn't there kind of like a disconnect between the two things there? Right? And it's similar with electrostatics. It's similar between magnets, where they aren't in direct contact with each other, and yet stuff still happens. You know what I'm saying here? So what physicists and scientists in general did is they came up with a word to help describe why this action at a distance was occurring, and they called it a field. Certain things possess a field and certain things don't. Okay? Now, everything possesses one type of field for sure that we've already talked about. Gravity, right? Everything has a gravitational field. I have a gravitational field, my keys do, all of you do. However, our gravitational fields are very weak. Right? The only reason why a gravitational field would be stronger is because either the distance between them is very small, that would increase the amount of field strength, or the size of the objects is very large. Does that make sense? Which is why we notice Earth's gravitational field, right? But if you were to go to another planet and be on the surface of the Moon or Mars, there's still gravity there, but there's way less of it. Does that make sense? So what we need to do today now is talk about that same concept of a field and how it works from an electrostatics point of view. So let me start with my first slide here. We've already talked about how electric charges are similar to gravity. I've told you guys about these 4 fundamental forces at some point. One's gravity, one's the electromagnetic, one is the nuclear decay type force. You guys remember what the strong nuclear force was? it's why the nucleus stays together. I mean, even then, we still don't fully have a great explanation for why all these protons stay together, because protons don't want to be next to other protons, and yet they have to. If the nucleus just ripped itself apart, our universe would cease to exist, right? We would have no matter. So thank goodness for whatever the heck that strong nuclear force is, right? We know it exists. We're just not really sure how it works yet. Remember how I started our unit kind of talking about how we can see the effects of the wind, but like we have a hard time describing it, right? You know, what is wind? Wind is really just the kinetic energy and air particles that hit you, right? We can't see it, we can study it, but we can study it indirectly. Same thing with a lot of these forces. I can study strong nuclear forces. I know something must be there, right? But setting up a lab to test it, I mean, that's what's challenging, right? Anyways, I digress. I'm getting off topic. Okay, so I need you guys to know this guy's name. Michael Faraday. He's going to come up again as he had huge contributions to physics, especially in the electromagnetic unit. But he was the guy who we quote having come up with the idea of a field. Okay? And then this is actually the definition we've used for fields before. This one isn't new. Okay? A field is a 3D region of influence. It's got to be in 3 dimensions. Okay? We are currently on one side of Earth. Gravity is pulling us down. Right? But people in Australia or New Zealand are also being pulled towards Earth. But they're, I mean, if you imagine it from a 3D point of view, if we're on top up here, there's no real top. You know what I'm saying here? They're getting pulled down, I guess. But people on the other side of the world, they're getting pulled up. It's got to be in 3 dimensions, right? It's got to go from all directions. So the same thing will apply to our electrostatic stuff. Here's the 2 words I need you guys to know, though. There is still scalar and vector. You guys can read my examples here. Heat, we actually consider to have a field. So heat from a fire. As you move away from the fire, temperature is going to decrease. But would you throw a direction on that? Does that seem logical? I don't know that I'd say that heat on its own, energy is not a vector quantity, right? We don't attach a direction to it. But like say gravity we can at least put some sort of direction to. Up, down, left, right, north, south, east, west. You know, even if we're looking at a big picture like a planet, you know, at least we can kind of put some sort of arrow direction on it and try to attach a direction. So here's the biggest thing I need you guys to start working with, though. Fields are not forces. Okay. What is the field strength of gravity on Earth? 9.81, give or take. But that is not the force amount. What do you have to do to 9.81 to get a force? Multiply by mass. So there we go. If the field strength of gravity on Earth is 9.81, that's not a force. To get a force, you have to multiply by a mass. Whose mass? The Earth's mass? Our mass, right? Whatever the object is we're talking about. Well, we have a similar principle that we're going to have to work with in fields for electrostatics now. When we find a field strength, that is not a force, but it's going to be very similar, but we're still going to have to multiply by something else. We're going to multiply by a charge. Okay? So I'm going to show you that over the next 2 slides here. So, electric charges then, we consider them to be vector fields. Okay, so we do care about direction. Direction matters greatly. Okay? And the idea is that if you bring some charges near each other, their fields would actually interlap. And you'd actually have there would be a force of attraction between each other. And so this is how Faraday thought that he could transfer force without actually touching, is that there must be some imaginary field going between these things. I pulled this diagram off the internet. This is an example of what a field might look like, where this is a positive charge, obviously this is a negative charge. If you were standing right over here, the field lines describe what would happen to you. So if you were standing over here, can you guys interpret that it means that you would be sucked towards the negative charge? Does that make sense? Right? Whereas if you were standing right here, you'd get sucked that way. Or if you were over here, you'd actually get pushed that way. What does a field represent in terms of positive or negative? Does a field represent what a positive would do or what a negative would do? Let me say that again. Does the field represent what would happen to a positive charge or a negative charge? Positive charge, yeah. Here's what happened. when we decided to work with fields, you know how it's a vector field, right? Direction matters. Okay. I can't just all of a sudden change the direction to outwards. That would make a difference, right? We had to choose one or the other. We had to choose, is a field going to be based on what a positive would do or on what a negative would do? And I don't think they flipped a coin or anything, but they just had to randomly choose one, right? And so they chose what a positive would do. So when we consider what an electric field is, an electric field basically refers to what would a positive item do in this location. Does that make sense? Why does that not matter so much for gravity? Why does the gravitational field for my keys not really need that same sort of logic to it? Which way is the gravitational field pulling my keys right now? Just down, right? There is a direction to it, right? But we don't need to consider the positive versus negative because gravity only does one thing. Gravity attracts. That's it. Gravity doesn't repel. Okay? Whereas electrostatics has the ability to repel and attract, depending on the type of charge. So flip a coin, didn't actually, right? But flip a coin, pick one. We've decided to say that a field is based on what a positive would do. Okay? Find your assignment. Now that we know this information, let's answer number 3. In what direction would the electric field be at a point halfway between the particles? If you were a positive charge, because we had to pick one, just randomly, a field is going to be described as what would a positive do. If you were right here as a positive charge, which way would you want to be attracted? Because you would want to be attracted towards the negative. And, even better, you would also want to be repelled from the positive. Does that make sense? We had to pick a direction, right? We had to pick one of them to go with. So, positive is the one we picked. Does that make sense? So, that's the definition of a field here. Where are we going? Okay, so that's kind of what I have written in this next slide of notes here, if you guys want to kind of read through the words. What we use is called a test charge. Okay? The test charge is basically what would happen to an infinitely small positive charge. And then the field lines basically describe, well, where would you go based on certain locations? So let's fill in these blanks here. If a positive test charge moved towards an unknown source, what would the unknown source charge be? Good. Which means if the positive moved away from, then the unknown one would be positive to however you spell that. Sure, positive. Right, and this is my diagram down here. You guys can hopefully see this, right? If we have an unknown charge, if a field line is being drawn towards it, we draw our arrows towards negatives and away from positives. Okay? We just had to choose one to go with. So, I don't know, Faraday probably made that call. So here's some more diagrams to kind of show you how this field would work. This negative charge right here, I have a whole bunch of arrows pointing in towards it. Because, again, I'm being redundant here, but what would a positive do? A positive would be attracted to that negative from all dimensions. Now, this is on 2D paper or whatever, right? But this would even happen in 3 dimensions, right? If this was a negative charge right here, if you were over here, it would go there, right? If you were over here, it would come there. If you were down here, it would go there. Does that make sense? But if it was a positive charge, well, we still draw the same lines, right? The line is still in the same spot. It's just the arrow points the other way. Sound good? Awesome. Okay, one thing that you guys are going to have to get familiar, though, is not working with necessarily just one field, but what happens when fields interact with each other? What if you have a positive and a negative and another one over there and another one over here? Then what happens? And these make some super cool diagrams sometimes. So I have some pictures I'll show you later, but here's what a field would look like if you had a positive and a negative. So let's just consider a few possibilities again. What if you were over here? This is your test charge. Test charges are positive, right? Well, what would a positive want to do? Well, a positive would want to get the heck away from the other positive, right? But why is it curving off to the side? Because there's a negative over here. Wouldn't the positive want to be drawn to the negative? But like, hopefully this makes a little intuitive sense. This positive wants to get towards that negative, but it's not going through this positive, right? So in a way, doesn't it kind of have to like take the roundabout way of getting there? Like it has to get pushed away from the positive charge. The positive keeps pushing it away until finally it can kind of get sucked into the negative. Does that make logical sense? So that's why some of these lines eventually start getting curved. Right? I wrote down here with my note, field lines tend to be straight, but they're going to be curved in other places based on the fact that you have two different charges. Right? If you were sitting right here, this was your positive test charge, you're going to want to be pushed away from the positive, but you're going to kind of want to be pushed towards the negative. The closer it gets towards the negative, right, like you can kind of see, well, it's going to push him that way, but then he'll pull him back in. That kind of explains the bend, right? Okay. So here's another photo. This one's a bit different though. The change here is that this is positive and positive. So that's not positive and negative, it's positive and positive. Let's talk about what's going to happen here. If you were just your testing charge over here, well, you just get pushed away, right? But see how there's kind of a dead zone in here? Doesn't that kind of make sense here? Where you're kind of stuck in limbo right here. Let's say that you were right here. What would happen to a charge that was sitting right there? Would it even move? No, right? Because what would happen is this positive would try to push it that way, and this positive would push it that way, and it's kind of in limbo, right? Because there's no reason for it to move anywhere. As long as these two positives are the same charge, right? If one of them was stronger than the other one, then the force would cause one to kind of win the pushing battle. If that makes sense? So you can get some pretty cool field diagrams. Right, here's a whole bunch that I pulled out of your textbook. Here's just a single solitary negative, a couple of negatives, a negative with a positive. Eventually, we're going to talk about what happens when you have a couple of plates across from each other. You know what a couple of plates across from each other actually creates? Looking at you guys in year 12, because we did last year chemistry. A positive and a negative pole of some kind. Yeah, a battery. There's actually going to be some overlap between this and the electrochemistry. Remember how last year we talked about anodes and cathodes? Right? Now when we did them last year, sorry, this isn't applied to you guys yet. But when we did this last year in electrochem, right? We ended up talking about the anode and cathode in terms of an electrolytic cell. Right? Similar properties here. We're going to talk about voltage and current and that sort of stuff because remember like Leoa and Gerk and that sort of stuff? Loss of electrons, gain of electrons. Right? Really what would happen here is if you were a negative, I know the fields are meant for positives, right? But if you were a negative, negatives leave the positive. No, that's not right. Negatives would want to leave the negative terminal and go towards the positive terminal. You remember that stuff? So, anyways, there's gonna be a lot of similarities between the electrochem unit from chemistry and this unit here. So we'll do that next year. Sorry. All right, moving on. Okay, let's get to the math. So I want to show you guys how to use the two new formulas. E with the vector on top is electric field, right? I have the note down here. E on its own energy, E with the little vector hat thinger on top, that makes it a vector, which makes it a field strength. Poorly chosen to use E in both cases, just make sure you're careful. Okay, so here's how this works. To find the field strength, take the force and divide by charge. I'm going to show you a parallel here. If I want you to find gravitational field strength, wouldn't that be the same thing as finding the force of gravity, which is really just mass times gravity, right? And dividing by mass? Wouldn't that kind of be the same thing? Can't you visualize how that would cancel out your mass and then you'd have just gravity by itself? So this is where we're going to start. If you want to find the field strength, what you do is you find the force of attraction between them, and then you divide by how much charge you have, though. But this is the charge on the test charge. Let's talk about why it's the test charge. If you want to figure out the field strength of Earth, right? You know how you do mass times gravity? do you use Earth's mass, or do you use your mass? You use your mass. Does that make sense? So in a similar sort of scenario, I am now the test charge. So if I want to figure out my force of gravity, I'm the test charge. When you want to use this formula here, you have to divide by the charge of whatever your test charge happens to be. So don't divide by the charge of the actual object providing the field. Divide by the object that is the test charge object. Let's try it. Okay, we've got a 3.7 Coulomb test charge. Stop. What does 3.7 coulombs really mean? It's a lot of electrons, right? There's that number that we wrote down there, but it's a lot of electrons, right? By virtue of it being a 3.7 Coulomb test charge, though, is it actually a lot of electrons, though? Or what's a better way of phrasing it? If it's a positive charge, is it actually a lot of electrons? What is it actually? It's something that's lost a lot of electrons. Does that make sense? Because if it is positive, the way for it to become positive is that it lost a whole bunch of electrons. I'm gonna try to remind you of this as we start, and then eventually, hopefully, you'll intuitively remember that, so we don't have to talk it through every time. But if you have a 3.7 Coulomb test charge, this is a positive, which is good because we always make our test charges positive. But it really is not electrons. It's actually the lack of electrons. Okay, it's placed 2.7 meters to the right of a negative 7.94 Coulomb source. This one does have a lot of extra electrons. What's going to happen to these two charges? Are they going to want to attract or repel? Attract. Okay. They've actually told us the amount of force that's acting. Let's see if we can figure out the field strength. So, new formula, electric field strength with the arrow on top. Do not forget that. It'll save you headaches if you can remember. Is equal to the amount of electric force, that's a vector, over the amount of charge. We have to do two numbers and divide by each other. We need to take 3.62 times 10 to the 10. We have to divide by a charge. Which one, though? The 3.7. Because it is the test charge. That's all I need. So sometimes you'll find in this next sort of sections that we're doing here with these different abstract sort of things, the math is super easy sometimes. The harder part is just wrapping your head around it. It'd be nice if that was in scientific notation. I got a 9.78 number. Although you only get 2 sig digs, so 9.8 times 10 to the 1, 2, 3, 4, 6, 7, 8, 9. You guys get that? Okay, let's talk units. The units for electric field strength are newtons per coulomb. That's probably one of the first standard units that we have, newtons per coulomb. However, there's a few other ways that it can be written. Oh, good call. Let's do that first before I forget. Let's start with the diagram. It is placed to the right. Okay, so the negative charge, this one is on the right of it. So it's going to want to be attracted inwards. So it's going to the left. You guys in agreement on that? I got that right? The positive test charge is placed to the right of the negative, so therefore the field would be pulling it in. Does that diagram make sense? I want to focus on newtons per coulomb for a second, though. A coulomb on its own is a base unit. Okay, a coulomb is basically a lot of electrons. You can't break a coulomb down into more fundamental units, but you could with a newton. What is a newton equivalent to? Yeah, so it could be a kilograms meters per second. And then what you could do is you could throw like the seconds and the coulombs together. So this would be an alternate way of writing it. A kilogram times a meter over a second times a coulomb. I missed that? You're right, second squared, isn't it? Thank you. Good catch. So they like to throw a question on diplomas where they make you practice like funky unit conversion things, where they might give you a Newton or like a watt or a joule or some of those sorts of crazy units that we see, and you have to like convert them around a little bit. So, but a coulomb is a base unit, so you can't really mess around with a coulomb anymore. First one's pretty straightforward. Let's try the next one. Oh, actually, I have a thing comparing them. So let's talk real quick again, just recap about the differences and similarities between gravity and electrostatic fields. There's one big difference. Gravity only attracts. Electrostatics attract and repel, hence the need to know whether you're using a positive or negative test charge. That's all. So, you guys can read that? Let's move on. Okay, next example. Positive test charge of 3.7 times 10 to the 6 coulombs put in an electric field with the strength. Let's figure out the force. This is pretty straightforward. Right? Electric field strength is this. Electric force is this. Charge goes there. This is 2.3 times 10 to the 3 newtons per coulomb. Don't know this guy. I got 8.5 to the minus 3. Awesome. The unit will be newtons. Hopefully you guys can see why it'll be newtons, right? Because if you take this newtons per coulomb number and times by that coulombs number, won't those coulombs end up canceling? We should be careful with directions again though, because these are vectors still. So I'm just going to draw a quick picture here. The electric field is going outwards. What is the positive or negativeness of this object? Positive, yeah. Right? And then if the force, if the field strength is outwards, then the force on the positive test charge is also going to be outwards, whichever way that ends up being. Up, down, left, right, north 3760, north 37 south, or whatever we do. Still good? Awesome. Okay, well, we've actually kind of realized that really this formula we just did here, we may as well make some like substitutions where we've kind of merged two formulas together. Let me see whether I can try to explain how this happens. Here's one formula, here's the other, and using a systems of equations, they managed to turn it into this one. Okay. You see how Fe is in both of these two formulas right here? If I were to take the Q and times it up there, you'd end up with the formula of EQ equals Fe, which means that these guys here would equal each other. You know what I'm saying here? And then see how there's a Q on this side and a Q on this side? All we've done is we just canceled one of the Q's off, which left us with E equaling K Q over R squared, only I think I canceled the wrong Q. Remember, the Q we have to cancel is the, this Q right here is the test charge Q. So the one that's left now is the source charge Q. You're going to want to write this down in your data book so you know which one is which. It's kind of like in the gravity formula, you know how one of the masses is your mass and the other mass is the mass of the Earth. You just have to make sure you know which one goes where. So in the E equals KQ1 over R squared formula, that Q is now the Q of the source, the thing that's providing the field. In the formula we learned just a few minutes ago, that Q is the Q of a test charge, which is always positive, by the way. Does that make sense? In one formula, it's the test charge. In the other formula, it's the source charge. You guys get what I mean when I say the math is actually going to be pretty straightforward here? It's just plugging numbers in, right? The harder part is just don't screw up the theory side of it. Make sure you understand what numbers go where. Alright, so let's try an example. I'm going to give you a ball that has a whole lot of excess electrons because it's got a negative charge. 3.0 10 to the minus 6 coulombs means there's a lot of excess electrons. We're going to figure out the magnitude and direction of the electric field 30 centimeters away. So our new formula, electric field strength is equal to K Q over R squared. Remember what K is? Awesome. 8.99 times 10 to the 9. The harder part is remembering what the stupid units are again. It's, was it newtons over coulombs squared meters squared? I always forget. Newtons meters squared over coulombs squared. Yeah, I got it. That's an N, by the way. Newtons meters squared over coulombs. Okay, so there's our K value. Then we get it times by our charge. Okay, you know how sometimes these formulas here have absolute values on them? See how the one we're working on actually has absolute values around the sides right here? Okay, let's talk about this for a second here. Why does the one below it not need absolute values around it? Good, hold on, Darian. The one below it, the E equals Fe over Q, does not need absolute values because the test charge is always positive. So we have no reason to flip a negative back to a positive. Okay? However, on this one here, the reason why we throw an absolute value around it is because I don't really care whether it's a negative or a positive. We'll figure out the direction later. Right? So even though it says it's negative 3 times 10 to the minus 6, who cares? Just make it positive 3 times 10 to the 6, and we'll get to that negativeness in a bit. Alright, and then last thing, we need to divide by 30 centimeters, but we got to convert that into meters, right? So that'll be 0.3. Yeah, 0.30 meters squared. Don't forget to square the 0.3 number. How many of you were making mistakes where you forgot to square the velocity in like the kinetic energy formula? Any of you guys do that? I think on this formula here, if you're likely to make a dumb mistake, it's that you're going to forget to divide by r squared. You're just going to divide by r. So try to make a mental note. Don't forget to square the stupid r at the bottom. Look at the units. The meters squared will cancel with that meter squared, right? One of these coulombs will cancel with that coulomb. What units are you left with? Newtons per coulomb. I got 2,996 repeating, so that makes it 3.0 times 10 to the 5. You guys good on that part? Okay, now let's talk direction, right? So, like I was saying with the absolute value, the reason why there's an absolute value sign on this formula is that you could have a negative or a positive. I don't care whether it's negative or positive, just use a positive. And now when we're done, let's consider direction. So let's draw a quick little diagram here. You have an object here which has a negative charge. Which way do we draw arrows when it comes to negatives? Away or towards? Towards. If you forget, you just have to memorize that a field, we just randomly chose to make it what a positive would do. So what would a random little positive guy do? He would go towards the negative, regardless of whichever location it was in, right? So, I don't know, towards, something like that. Sound good? Awesome. Okay. Well, this is very similar now to where we were yesterday. I've introduced a formula to you. They're more or less straightforward. Here's the part where it sucks. Take a look at the next couple of slides. You're going to see the parallels. This slide here, we're going to do something in a linear direction where we just have to combine the fields to each other. And then I'm going to make you do it in 2 dimensions, or 3 dimensions, or 2 dimensions. Right? 3 is too much. We don't go in 3 dimensions, but 2 dimensions, right? So you guys can see where this is going here. It's actually fairly straightforward until you get that one random straight question in 2 dimensions. It's going to take you 5 to 8 minutes, right? Be prepared for it. I don't know whether it'll be a force, a field, momentum, or something else, but you're getting something in 2 dimensions. Anyways, let's try this one then. This one's easier. We want to find the electric field strength in the exact middle of these 2 charges. Do exactly what we did yesterday. Find the 2 electric field strengths. They are vectors. Vectors can get added and subtracted from each other. So we just have to figure out which way the fields are going. So let's consider the 3.9 charge. Which way would the field be going with a negative 3.9? Towards or away? Towards, yeah. So this guy is being pulled towards that guy by this charge here, right? However, over here, this 1.2 coulomb is also getting pulled towards that guy. It's right in the dead center middle. Who's going to win this fight? The 3.9, right? Only because it's bigger, right? If it wasn't dead center in the middle, we'd have to consider distance as well. So I do know which way this is going to go. By the time we're done, it's definitely going to the right. Does that make sense? Because this one is going to beat out this one in terms of its like fight for electrons. But we do want to find the field strength. So essentially we have to find the electric field strength for the first one, the electric field strength for the second one, and when we're done, we're going to take the second one and we're going to minus the first one, and that will give us our answer in units per coulomb. You guys get what I'm saying here? So give it a try. Do it without me.
Management and all that in your classes?
For one of the field strengths, I got 128 to the 11. You guys get that one? Okay. And the other one I got 416 and change to the 11 as well. You guys get something like that? Okay, so once you find your 2 field strengths, keep in mind, field strengths are vectors. Right? So by virtue of them being vectors, vectors can be added and subtracted to each other. However, similar to momentum, you have to add x direction vectors to x direction vectors, y direction vectors to y direction vectors, and when you're done, if it's not in the linear direction, you might have to do a hypotenuse. Thank goodness for this one here, they're all in the x direction, right? So just subtract the 2 numbers, you got your answer, right? Let me know if you don't get this number. Okay, so only 2.9 to the 11. Is it going? Tom, that makes sense to you?
Yeah.
You're good on this? Cool. Was it good, the linear one? Are we starting on the next one already? What should I say? Okay, start on the hard one. So, in terms of concept, you're going to have to find the electric field strength from A to P, from B to P. You're going to have to break it up into an X direction, into a Y direction. You're going to have to probably do some adding or subtracting to the X direction, some adding and subtracting to the Y direction. Once you have your net X and your net Y, you hypotenuse them and find an angle. Yay, good luck. What's that? No. Alright, I'll give you 5 to 8 minutes. That's pretty much all you have though, right? So, speed does matter.
This is what I did with them yesterday. Like to give them a chest shot on their own because they don't even need me at this point, right? Like they're so ahead of the game. So I'm gonna freeze the screen here. Okay. Yesterday I did such a bad job. We were using Pythagoras' theorem, and I wrote it properly in my calculator. I did a squared times b squared equals c squared on step 1, and so all of my work was buggered up. It was so bad. So I do a better job today. So I'm freezing the screen here. Tom will actually be able to see what I'm doing here. So I'll try to like do all the work on here for them. I started doing this recently, and then I'll just let them compare later. But like they know what they're doing.
Well, that's
So the formula was KQ over R squared. So it's 8.99 times 10 to the 9. Let's see, this guy is 2.10 times 10 to the 6, and the distance between them is 4 times 10 to the minus 2. You following this, by the way?
Yeah.
Does this make sense?
Mm-hmm.
Nice. I do say this makes sense a lot.
Yeah,
Right.
I have a habit of doing that too.
Yeah. When I was in my PS2, my practicum teacher drilled it into my head, for better or for worse. She said that you need to like always be checking. How did she say it again? It was show, don't tell. That's what she always told me. Is that you need to try to show them what to do, but don't just tell them the answer.
Mm-hmm.
And it was always like kind of in the always kind of in the way of saying like, well, how do you know that they get it, right?
Mm-hmm.
And I've since realized that like sometimes the answer is you just know. Like you work with a kid long enough, I can look in Darian's eyes and be like, do you get it? And he's like, yes. And I'm like, okay, I'm good, right? And sometimes like a kid will, tentatively be like, yeah, but like they just want to like get rid of you kind of thing, But like that is what I say. That's like my go-to, like, check for comprehension thing, so that I go, okay, if you're good, I'll leave you alone. Because sometimes I think as teachers we like try to micromanage kids too much, and we don't give them enough time just to go be and just do their own thing. Because like even as I was looking at this example here, I'm looking at them going, why are they still writing stuff down? They should have done this example a while ago. And I realized they're on the next one.
Yeah.
They're being polite. They don't need me. Which is a dynamic that's unique to high school. Like when you teach junior high courses, it's very, very different, obviously.
Right.
Different dynamics between different kids. 3.00 times 10 to the minus 2 all over. Shoot, I screwed that up, didn't I? The distance, the charge, there it is 1.50 times 10 to the minus 6. 3.00 times 10 to the minus 2 squared. It's actually one of the things I had the hardest time with. Is I think all teachers do. They have a tendency to want to micromanage and go check and try to interject themselves.
Right.
Which I mean, when I went through my PS2, and my teacher was always, go around the room and talk to kids. That's always a good thing, right? There's never a bad thing in talking to kids, but I think there's a lot of value in recognizing, the fact that we need to teach kids independence and being able to do it on their own.
Right.
And when they reach that point of getting there, being like a helicopter parent version of a teacher. I don't think most teachers really ever kind of get to that realization, because we're always just taught, well, we're the sage on the stage who's supposed to be doing stuff, right? Mm-hmm. One of my favorite types of classes, I did this years ago with that one group of kids I was telling you about, some of your friends there. Mm-hmm. I ended up doing a class one day where I didn't do anything. Like, I didn't start the class, I didn't finish the class, I did no anticipatory set. I mean, if you were to evaluate the class from like a lesson plan point of view, it was horrible in terms of that stuff. It was the best class we ever had. Like, I had talked with them before the class about how, what I wanted them to do the next day. It was just going to be work stuff. They knew what to do. They were independent. And so they just came in, they started working. When the bell went, they left. I never addressed the class as a whole once the whole time. And after I tried that one day, I was like, oh, this is really cool. So like I try to do that as much as possible where, I try to empower them to just take initiative for their own learning.
Right.
And I mean, I went over and helped them and I talked with every kid in the class multiple times during the class, but I never was like the look at me, I'm directing traffic kind of thing. All right, what am I up to here? We got this. So now we need to find the X and Y components. So we need E1X, E1Y. E1X equals E1 times the cosine of 36.9 degrees. Cosine of 36.9 degrees. 9, 4, 3, 5, 7, 7, 9, 3, E1Y is E1 times the sine of 36.9 degrees. One of the things that I really like about teaching in this school is just the fact that I get to teach these kids so often. So like I can talk with those guys about chemistry. Those are my grade 12s, by the way.
Okay.
They're actually like they're about like I've taught the grade 12s Chem 20 and Chem 30 already, and Math 20. I'm doing Math 30 with them right now. And then so these guys, Chem 20, Chem 30, Math 20, Math 30, Physics 20, Physics 30. These guys are on time number 6.
Oh wow.
So I've had them 6 times already. And these guys right here, I had them in Science 10, Physics 20, Physics 30, Math 20. So these guys are number 4 only. But we know the routine.
Right.
You know what I mean? So you don't have to explain what we're doing. Like they know exactly what to do. And if you can kind of build in that sort of routine, that just makes things flow so smoothly, which is a cool thing about being in like a smaller school. You said you went to a K-12 school?
I did, yeah. There's about 120 of us from K-12, so it's pretty small.
Yeah, you get to know everybody then?
Yeah. You know everybody's extended family and everything.
Yeah.
I found it a small school.
It's nice. Where is that? The 149 number times the sine. Okay, we got that. So let's think about this here. This guy is negatively charged, so the field's going to go towards him there. So we're going towards and towards. And this guy was positively charged, so we're going away. So that means on this one here, we're going away and away. So our x's we need to add to each other. So we have x that adds and x that adds. And then, let's see, I did that right? So this one's coming towards, this one's coming towards. And then positive, this one's going away, this one's going away, so I need one of these to go up, one of these to go down, so that was E1Y, E2Y. Yeah, totally. Okay, so X direction, it's going to be my 9 number plus my 7 number. You guys have an answer yet? Okay, give me 1 second. I'm almost to this point here, and then we'll have to compare. And hopefully, I didn't mess it up today like I did last day. No, let's skip the angle. You guys know how to, though, right? You just inverse tan your x and y. Let's just find the magnitude of it for right now. I mean, it doesn't take a while, but... Oh, I used the wrong numbers. Shoot. Okay, hang on. In the x direction, I need the 9,000 number. There it is. Plus the 8,000 number. Okay. 1,843,2075. In the y direction, who wins? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7, 8. Okay. That one goes that way. That one goes that way. Y was going up. That was going down. So that one wins. So I'm going to have one go up. So where are those numbers again? Okay, let's see if we get something as done. Yeah, I definitely do the work along with the kids here. I mean, I have no fear of making mistakes along with them because we just those learning experiences.
Right. I think I squared it close.
Okay, I got an answer here. You guys want to compare?
Yeah.
Okay, so let me unfreeze the screen here and we can walk through this step by step here. Okay, let me see if I can highlight certain numbers. Here's what I did first. I broke everything up into x's and y's and hypotenuses. So first I called this one E1 over here, and this one over here I called it E2. Okay, and in terms of values, I plugged in 899, these numbers here, and I got a field strength on one hypotenuse of 117, and I got a field strength on the other hypotenuse of 149. You guys have similar numbers on that step? Cool. Okay. Next step is I needed to break them up into x and y components. So I drew one triangle in here in purple, and I didn't actually draw one for the other, but let me draw it in here. Maybe I'll draw it in red. Then I'm also going to want one like this as well. Okay. And in doing that, I found an E1x and E1y, an E2x and an E2y, and I use sine and cosine to find those four values, and I have those sitting right here. So compare yours to mine. Let's see if we have the same thing. These are the four values I found when I broke them up and using sine and cosine. Still good? You guys are nodding at me? Okay, next is the hard part. Next we have to consider direction, okay, and what's going to happen. So let me go back up to the original diagram. Let's talk about the directions. Okay, this guy right here was a negative charge, right? So a positive would want to be attracted towards it, which means that this one right here is going down, and this one right here is going towards our left. So I wrote those with some arrows over here. I drew that this is a downward number, and this is a leftward number. That's a word. I make up words all the time. Okay, and then for this one right here, I said this is a positive charge, so therefore a hypothetical test proton positive, we want to go away from it. So it would want to go that way, which means that this one would want to go up and over. Does that make sense? So in doing that, I drew this one over, and I drew this one up. Still good? What that means then is in the x dimension, you have to add your numbers. In the y dimension, you have to subtract them. And when you figure out who wins, the one going up ends up winning, I believe. So I did that math, And I drew that kind of over here where this was what I had as my net in the x direction. This was my net in the y direction. Pythagoras theorem, I got 1.9 to the 6. Do I get 3 sig digs? I get 3 sig digs. Thanks, guys. Good catch. 1, 2, 3, 4, 5. No, 7. I can't even write it. Okay. 1.91 times 10 to the 7 newtons per coulomb. Do you guys get that? Anybody?
Can you explain that last part again?
Sure. Okay. So let's go back a couple steps here.
You subtract and add with 1.
Okay. So you got to consider direction at this point, Darian. Let me erase a whole bunch of this mess that's on here. Okay. So you're good up to the point where you find your 4 x and y values? Okay. So then we got to figure out whether we should be adding or subtracting. So this guy right here is a negative charge, correct? A proton test point, a positive, would be attracted to it. So this should get pulled that way. Which means that if I consider it's like its triangle right here, it means that this is getting pulled down and this is getting pulled that way. So what I did is over by these numbers that I found, I just drew an arrow saying this one has to go that way and this one has to go down. I just drew arrows to help keep track. And then for the other one, which I kind of drew like this in my head, this was a positive. So a positive is going to want to repel. So it means that it would want to go that way as its net. In terms of its 2 independent directions, though, that's going to mean it's going to want to push out and up. Still follow that? So I drew that over here. This is my way of doing that. I drew an out and an up. So when I had to combine them, this x direction and this x direction are both going that way. So I added these 2 numbers to each other. And when I added those 2 numbers to each other, I ended up getting that number down there. Okay.
Sean,
Yeah,
do you want us to include angle or is that relevant?
We should normally, but I told these guys, we know how to do that, right? Just inverse tan those 2 numbers and you'll find your angle. So.
Okay, I got the right answer, so can I go?
Yeah,
I got
we're good.
the right answer, so-
Okay, let's log in tomorrow just briefly to say hi, but tomorrow is a work day.
Okay, yeah, well, I've got Sabre Day, so I won't be logging in.
Oh, you're not even here. Never mind. Okay, have a great week off. We'll talk to you next week, Monday.
Alright, sounds good.
All right,
See
see
you,
you,
Sean.
Tom. Okay, sorry, you're still caught up with me here? So then, since this one was going down, this one was going up, first I just figured out which number was going to be larger, and it looks like this number is larger than this one here. So then I took this one and I subtracted this one. And when I subtracted those numbers, I got this value here, meaning that it goes definitely this way, but mostly like a little ways up. And then I hypotenused to find the hypotenuse value. And then that's where we are there. If I needed to, like Tom was asking me, we should have calculated that angle. I just figured, like, you guys know how to, right? You just inverse tan these 2 numbers. Okay, I guess passing final thoughts on the concept here. You guys know how to use the formulas, right? Like, the formulas on their own are straightforward. In a linear direction, it's also pretty easy. You just either add or subtract. It's these 2-dimensional ones, right? Where you have to be prepared that you're getting one, budget your time. Ideally, you can save some time on some of those other theory questions where you just look at it and go, oh, the answer's A, and you move on. Right? But you're getting one of these. So as long as you know how to solve it, what I might recommend when it comes to the diploma time, guys, just pause for a second. When it comes to diploma, you might want to just find where that 2-dimensional vector one is and do it last. Right? Because they're all worth 1 mark, right? So you may as well rip through all the other ones because you know this one's going to take you 5 to 10 minutes. And you know that in terms of complexity, this is the one that's going to have the greatest shot of you just making a dumb math mistake, right? I think you guys all know how to solve it, but like there's numbers scattered all the way through this thing, right? So you may just want to leave these ones for last when it comes to the diploma. All right. Anyways, we'll talk about those strategies in June. You guys feel good? You have the concept here? Okay. We got like 10 minutes or so left. You guys can start on your assignments. Tomorrow I want to give you a work day so that you can try to get through as much of assignment 1 as you can. So the main things you should be able to do now are any theory questions involving induction and conduction. There's a whole bunch of them scattered throughout that assignment. and then questions involving the force formula or the two field formulas and the theory that goes along with it. Sound good? Did that make sense? I just said that a lot, didn't I? Okay.